After I recorded the last lecture and said that I was probably not going to do much on implementation and scatter a little material as I could over the last few weeks, I thought about it and decided I really couldn't do that after uh, teaching graphics so long and realizing how crucial this material is and to not because you're going to program it directly because most of this stuff is built in, but just really to understand what's going on inside of the hardware. Um, it's really I think important to do that. So what I'm going to do over this whole week is look at the various parts of the in what I call the implementation process: clipping, rasterization, and then finally some more discussion of what goes on with the display and color systems. And what I'm going to try to do is focus not on all possible ways of doing it. There's a lot more information in the textbook, but look at some of the key algorithms of two types. One, the types that are in the hardware built into the microcode of the GPU, and some of the more classic ways of looking at things. And I'll focus just on line segments and polygons. So for this lecture, will be about clipping, and it'll probably be a little further from what goes on in the hardware than our discussion of rasterization. But one of the reasons I like doing this is that if you look at the clipping algorithms, you'll see there's a lot of computer science in here. There's a lot of algorithms. There's a lot of cleverness in how you implement it. And some of the things you'll see is that you think an operation requires a certain amount of floating point computation, and it turns out you can often get rid of a lot of the computation, and that's how you can process these millions and millions of lines and polygons per second in a modern GPU. So for clipping, what I'll talk about in this lecture is clipping lines. There's some, even though we don't do as much with lines as we do with polygons, some of the ideas I think are really nice in it. And then in the next lecture, we'll focus on clipping and rasterization of polygons. So the first idea is with clipping is to see whether it's for which kinds of primitives is it hard and easy. If we think about a more general graphic system, one that might support text and curves and surfaces of various types, you could sort of get a hierarchy of how difficult clipping is. So if you look at curves, for example, there's a real problem here in that you really don't know. You want to get rid of the parts that are outside of the window. So here's a 2D view of clipping against a window. In 3D, we would clip against some kind of a volume. Although if you go think back to when we talked about normalization, where we converted everything to a orthogonal view by normalizing both for perspective and for uh, parallel projections, we could convert all of those to orthographic projections. Those are the things we're going to consider, and you can see that even from the 2D example, that curves can be very difficult. So, for example, for a curve here, which I might know analytically, I have a function that gives it explicitly. I may not know how many places it crosses over the edge of the window, or in 3D and volume, and computing them may not really be a feasible thing to do, because you might have to apply some complex numerical method to find where these intersections actually are. For something like a quadric, here's a little ellipse, it's probably possible, and we'll talk about quadrics more next week, and when we talk a little bit about ray tracing the final week. But then you can have something like this spiral, which would be fairly easy to define mathematically, but has just all kinds of intersections with the side of the window, and figuring out what part to keep and what part to throw away is pretty difficult, and probably not practical in a graphic system. So one strategy would be for curves to take them and break them up into little line segments, and then the kind of line segment algorithms that we'll be talking about today will work. But if you have a real graphic system, generally you're doing this at a higher level. You're saying, well, I'm going to convert curves into line segments, and that's the subject of what we're going to be doing next week. Now, text is kind of a special case, and older graphic systems that supported text often would distinguish text in terms of the quality of what you wanted to do. So, for example, in the lowest quality level, you could put a box around this text, which might have words or a whole string inside of it, and say, well, look, if any part of that box intersects the edge, I'll just throw it all away. In the middle was the idea that you would do that kind of thing for individual characters. So you'd throw away the B because it partly intersected its bounding box partly intersected the side of the window. Or you could do it really accurately and go into the representation of each character, and that's what you see over here, and then just clip out part of that letter. And that used to be a distinction. Now with OpenGL and WebGL, well, we don't have text primitives, and the nice thing about WebGL is you can, because it's part of HTML5 or supported under HTML5, you can use other methods to get text in, so we don't really have to worry about text. So let's start by saying, okay, here, if you had curves, what you've done is you've broken them up into a bunch of line segments, and if you have text, well, we'll deal with that outside of WebGL. So let's look in 2D first at intersecting line segments, and the brute force approach would be to say, okay, here's a line segment. It's part of an infinite line. I can easily intersect two lines together, and if you have the representation of two, say ax, of the form something like y equals ax plus b for each, you can solve for the point of intersection between any of these sides, the extension of these. Because if you look at this window, one way of looking at it is it's four line segments. Another way you can look at it, it's the area created by intersecting four infinite lines. So if you had those equations, you could sort of brute force your way through them, find all these intersections, and then find if the intersection was inside of this box or whether it intersected the side of the box like this line segment EF. And it's inefficient because every time you're doing an intersection, you require one floating point division to do that, because you have these two equations, y equals ax plus b. You put them together to find the y, and you solve for the x, and then you have to do a division to do that. And divisions in general cost you much more, not just much more than additions and subtractions. They generally cost you a lot more than a multiplication. And so it's brute force, it works, but it's not something you particularly want to do. Now, you can also notice, even with the simple case of line segments, you've got these four possibilities. You can have the line segment entirely inside, one point in and one point out, and then you get these two other cases. And the point here is that here, if you know both points are inside, you know the whole line segment is inside. If one is inside and one is outside, then obviously part of it is inside, and you're going to have to find this point of intersection. But it's not sufficient to say, well, if both points are outside, then the whole line segment is outside, because that's true for this line segment that goes through C and D, that goes from C to D, but it's not true of the one that goes from G to H, because a part of it actually lies inside of the clipping window. And mathematically, this is the hardest case to deal with in a clipping algorithm, and we'll see how we do that. So brute force is something we don't want to do. If it was just brute force, what people did, then we would just sort of stop the lecture here, but we want to do better than that. So the classic algorithm for doing this is called Cohn-Sutherland. And one interesting thing is that Sutherland is who Remember, Sutherland was the one who created the basic paradigm in the 60s of how interactive graphics would work, that you would interact with a display and that would change what was on the display, then you'd interact some more. But in order to do that, because he was building essentially the first large-scale graphic systems, he had to create a lot of the algorithms to do it. He wasn't just doing the theoretical high-end kind of stuff. He had to actually build the stuff. And so a lot of the algorithms he came up with were very, very good and are still as good as any other algorithms out there. So the Cohn-Sutherland algorithm is not only interesting in its own right, but it's historically important. So the idea here is that what we want to do is eliminate as many cases as we can that very, very quickly. And if you think about it this way, that suppose if you have a simple problem, it really, a simple problem being one that doesn't generate a whole lot of geometry, it really doesn't matter what your algorithm is because you don't have enough geometry to matter. The GPU is so fast it'll do that. But the real interesting part is when you have lots and lots of geometry and you really want to clip efficiently so you can do an application that's real time with that amount of geometry. So one of the things the Cohn-Sutherland algorithm does is try and eliminate as many easy cases as it can, and then just focus on the cases, the small, hopefully, remaining number of cases where you have to do more complex operations, where here complex means doing a division. So if we can quickly eliminate everything that might possibly require division quickly, that would be great, and then just deal with those remaining cases and find these intersections. So the idea goes sort of like this, is that what we're going to do is look at not the line segments for the window, but rather the full lines that determine the side. So you have 4 lines, and the equations are just, x equals x min on the left, x equals x max on the right, and similarly for the top and bottom of the window. So if we look at 2 things, we can argue the following. If both endpoints are inside, then we know that that line segment is inside. We don't have to do any arithmetic with it at all, and we can just send that line segment on to the rasterizer to be drawn. That's called acceptance in the literature of the clipping algorithms. Now the other easy case is this: if both endpoints are outside and on the same side of one of the 4 lines, then we know that line can be discarded, or we call that rejection in the clipping algorithm. So now notice, if you go back, see this case here for C to D is different because it's fully to the right of the right side of the window, while even though for G and H, even though G and H are both outside, they're not both on one side of any side of the clipping box. G is to the left and H is above, and that's not good enough to simply reject it. So, but what we can do is now we've dealt with all things like AB and all things like CD. So that's the first part of the Cohn-Sutherland algorithm. Now, what do we do? So this is case 1 and case 2. Case 3 is one point is inside and one point is outside. Well, for that kind of a line segment, we know we're going to have to do one intersection. The reason I say at least one is that if I look at, let's suppose Y max was over here at the top right, then I wouldn't know whether it's both above the top and to the right of the right side, and I wouldn't know which intersection to do first. So I would have to possibly do 2 intersections. I can intersect with one side and find an intersection over here, and then say, well, look, you're still above, so I have to do a second intersection. Think of that if you started with this point over here, and it was up here, you might intersect first with the right side, get this line segment, and then say, well, look, now that point is still above. So case 3 requires at least one intersection. Now the fourth case, the hard one, is you may have part inside, and then if it is inside, you may have to do 1 or 2 intersections, like in this case. In the case of this one, you got to intersect with the left side, and you have to also intersect above. Now, next part of this is, so that's just sort of an observation in which order we should do things in. But the second part of it is, how do we do this kind of thing efficiently? And what the Cohen-Sutherland algorithm said is, let's define an outcode that characterizes each of the points of intersection by whether they're above, below, to the right, or the left of the clipping window. And we'll have a bit, so we'll have a 4-bit number or a variable that where a bit is set depending on whether it's above or below, to the right or the left, where let's assume B0 is the one for the top, B1 is the one for the bottom, B2 for the right, and B3 for the left. So what that does is divide space up into 9 regions, where each region is characterized by this 4-bit outcode. So for example, all of the 3 regions above the clipping window, here's the clipping window here, everything inside is an outcode of 0, 0, 0, 0. Everything above has an outcode where the first bit is 1, and then the second and third bits are determined by whether it's to the right or the left. Likewise, in the middle, everybody has outcodes where the first 2 bits are 0, but it could be to the left, which would set B3 to 1, and it could be to the right, which would set B2 to 1, and likewise for the bottom 3 regions. Now, what do you have to do to compute these outcodes? Well, they're really simple. They just require subtractions. You just check whether the y of your vertex is bigger than y max to get the first bit. Well, how do you do that? You just do a subtraction. So that's easy to do, at least easier than carrying out divisions. Now, we now can reason for the other cases in terms of the outcodes rather than in terms of some floating point representation of the actual values of the vertices, because it turns out I can get a lot by just looking at the bit code. So for example, if both points are inside, the 2 outcodes are both 0, and I could check whether the 2 outcodes are 0 very quickly, and then I accept that line segment, okay, based on the outcodes. If I now look at, say, CD, now I say, well, how do I determine this requires an intersection calculation, because the outcode of one is 0 and the outcode of the other is not 0. And which bit is set will tell me which side I have to intersect with. So if you come back over here, you could say, well, look, if the line segment goes from somewhere in the middle with an outcode of 0 to some place where only 1 bit is set, then I know I need exactly 1 intersection. I intersect with the right. And if 1 is inside and the other outcode has the first bit 1 and the other 3 0, I'm going to intersect with the top of the window. Now the hard part, as we saw, was the one where 2 bits in the outcode are set and one of the other outcode is 0. Then it tells me, well, you're both above the window and to the right, so you can pick randomly which one you want to intersect with first. And what you do then, after you've computed the first intersection, is you go back and you say, well, what's the outcode of that new intersection that I computed? If it's non-zero, then I do another intersection. If it's 0, then I'm fine. We say that when you're on the edge, then you're inside. So if I had done, say, let's go back to say a case where this was up, where D was up here, then I could look. If I intersected with the right first, I look at the outcode over here, and if it's above, then I have to do an intersection. If it's down here, like with CD, then I'm finished. Okay, now let's look at the hard case. The hard cases are, how do you distinguish between EF, GH, and IJ, where in this case so these cases are actually 3 very different things. Notice for EF, you're fully to the right. For GH and IJ, you're both to the left and above, and this is where I have to distinguish. Well, how do I get rid of EF? Well, I can note that they have a bit in common. The bit that they have in common for the 2 outcodes is the one corresponding to being to the right of the window. So the test would then be to do the following: to just say, for if you do a logical AND with the two bit codes, what's going to happen if they have a bit code that is the same? Then the ANDing of the two bit codes together is going to give me something other than 0. And I say, well, if that's true, then throw away that line segment. If I get a 0 that says, well, now you have two outcodes there. One is on one side of the intersection and the other is on the other, and then I have to do the more complex calculation, and that's what I do for G and H. Is that for the GH and IJ, and now I say that the ANDing gives me 0, but I have to shorten the line segments and figure out what to do next. So this algorithm is something called sometimes called reentrant, because you do a check and then you go back in and take the result and apply the algorithm again to it. Now, one of the reasons, so you get a lot of efficiency with this because you've now been doing operations that are just totally bit operations. After you do those subtractions first, then you can just argue in terms of the bits, and it's very, very quick to do. And you're only doing intersections that you really would have to do. So you're not really doing any extra work anyplace in this algorithm. Now, one of the other reasons that it's so efficient is this: that if you think about having an enormous database that just consists, for now, of line segments, you generally don't ever do a display that has all of those line segments. And generally, the idea is that your window is very small compared to the size of the world and having all of that geometry in it. So a very small percentage of what you have in your database is really being displayed. If that's the case, then most of the line segments, let me come back over here, most of the line segments are going to be fully on one side of the window. That, think of this giant database with lots and lots of little line segments in it. Most of them are going to be to the right, to the left, above, below, and only a few of them are going to be these kind of difficult cases like GH and IJ. So the point, or even AB. So the point is that you're going to have to do, or CD even. So the point is that you're going to have to do very few actual floating point computations, because so many of the line segments can be discarded very, very quickly just based on looking at the outcodes and doing some simple bit operations. And that's really where the efficiency of the Cohn-Sutherland algorithm comes in. Now, the negative side turns out to be this, is that because you have to re-execute the algorithm when you do the intersections, for some, as we saw for some of the cases where you, for example, have a point inside and the other point is both to the right and above, re-executing the algorithm in terms of the execution of the code can be somewhat inefficient. You don't really want to have a reentrant stuff in there. So you can look at ways to get rid of that, but there's another algorithm I talk about in the book that turns out to be a little bit better when you put it in parametric form. So if you're interested in these kind of algorithmic things, then certainly take a look at that. One of the other nice things, and this is another distinction I made with all the algorithms I chose to put in the book and talk about here, is that I wanted algorithms that you can extend to 3D. And it turns out that the Cohn-Sutherland is very easy to extend to 3D. Notice that you're actually intersecting with planes instead of intersecting with lines. I'll get to that. But the first thing to note is if you look at the cube that you're trying to clip against. Now remember, we've done the normalization, so everything reduces to clipping against the standard cube. This cube is formed by 6 infinite planes. And we look at where they intersect, and what that leaves me is the cube. Each plane divides space in half, and I get this remaining little part. So the sides of this cube, actually the planes, divide space into 27 regions. It's sort of like, well, look at it over here. I can be in front, behind, to the right, to the left, above, and below. And that says, well, okay, use a 6-bit outcode. Do exactly what you're doing before, but add 2 more bits that have to do with whether you're above, past the maximum Z or on before the minimum Z. And so you get a figure that looks somewhat like this. So this is showing that you're less than Z min. Back here, everything is greater than Z max. So everything in front looks exactly like what we had in 2D, except for these 2 bits in the front that have a 1, 0 in front, and back here they have 0, 1, and then to the sides you're within the min and the max Z, so the first 2 bits are 0, 0. So this all works, and when you have to do an intersection, you have to do the intersection with a plane, and I'll just mention that briefly. Obviously not a too difficult problem. The real benefit of normalization really comes with when you start looking at this. If you had a general clipping region where you had a parallelepiped where the sides are parallel but they're not meeting at right angles, or if you looked at the frustum when you did perspective viewing, all of these planes are tilted, and so the intersection involves a lot of floating point operations. Now you could do that. You could say, okay, how do I do an intersection of a line segment with a plane? Well, you can sort of look at it here, and you can do this computation and say, okay, well, you can look at the standard form for the line segment going between P1 and P2. Look at it as a parametric form. So you have the standard parametric form that it's 1 minus alpha P1 plus alpha P2, and for every alpha I'm along this line segment. For alpha between 0 and 1, I go between P1 and P2. And then I can do the intersection with the plane, and the plane can be specified by looking at the dot product of the normal and to this plane. If you solve all those equations, we've done this before, you get a fairly simple equation for the value of alpha where it intersects, and now you have this, for that alpha you can now compute the x, y, z where it intersects. But if you look at this expression, there's a bunch of floating point multiplications in here, right? Because this is a dot product, so you have 3 multiplications up here and 3 multiplications down there, and we really don't like that. However, if you had done your normalization first, and here's where it really comes back in, and we weren't able to really show that well before, was if I had, so this example is for an oblique view. So if I come back here saying, well, in an oblique view, you're looking down from down out here. Here's your clipping volume, and the sides are relative to the coordinate axes are all tipped. That's the clipping volume for oblique viewing. But we had said, no, you're not going to do that. What you're going to do is you're going to first normalize the thing to be inside of this we're going to convert it to an orthographic view by doing a shear operation first, where we shear the data. Now, before, when we talked about this, we only talked about what happened to the object, and the object became, so if we had this nice little square here, or cube in 3D, and we sheared it, it had these tip sides, and the projection, though, orthographically of this object would give me exactly what I would have gotten if I had just done this in the original unnormalized space. So you can say, well, you don't really gain much here. Well, you sort of gain one thing, in that you only need one hardware pipeline that only knows how to deal with orthographic views, and that was our argument with perspective viewing. But we didn't really talk about this aspect, which is what happens is that when you do the normalization, the sides now become orthogonal to the projection plane. So now you really don't have to do this kind of an operation for computing the intersection. The intersection is actually trivial. If you want to compute the intersection of a point with the side of the window, you're simply checking the x's, y's, and z's against the sides of which it turned out all going to be plus or minus 1 when you normalize it. So you're just looking if x is bigger than 1 or x is less than 1. So the other real benefit of normalization turns out to be that it reduces clipping to a very simple problem that doesn't require a lot of arithmetic or floating, in particular floating point arithmetic. Okay, so in the next lecture, what we'll see is, well, what happens if now we're looking at polygons instead of looking at line segments, and we'll see it's another reason why first reducing everything to triangles is going to be so important.